Okay, let's start. Good morning. So this week we're going to start talking about series infinite sums when you can add up infinitely many terms. Maybe those terms are just numbers or maybe they're functions. We're going to have to look into both situations. So I'm going to be taking attendance today. Two items, I guess. So midterm 2 is graded. I'm fairly happy. The average is around like 83, 84. So that's good. Another thing is that I forgot to upload problem set 9, I guess, on Friday. I uploaded this morning, but it's still due this Friday. So because there isn't that much time, it's significantly shorter than usual. There are only 3 problems in it. It's relatively easy. One of the problems we discussed on Wednesday last week, if you were there, you're going to find it familiar. It's this different statement for the mean value theorem. So today, what we're going to do is we're going to finish the proof of this change of variables formula. We had started the proof of this last Tuesday. So one version was for signed integrals that we had proved completely. And then the second version was for unsigned integrals using a diffeomorphism phi for the change of variables. This is the more sort of natural version, quite possibly. So I'd like to finish the proof of this, then discuss just a little bit this issue of improper integrals. And then tomorrow, we're going to do some interesting stuff. I would like to discuss what is called weak derivatives. It turns out that there's a way to do things in a weaker sense. For instance, you have, let's say, a differentiable. You have a function that is not necessarily differentiable, but sometimes you're still able to differentiate it in some weaker sense. So we're going to discuss that. It's quite nice. It's basically an application of the integration by parts formula. Before I start, are there any questions or comments? Okay, the situation was this. Let me just draw the picture because it's rather verbose to state the change of variables. You have 2 intervals. You have one interval I, another interval j. And this is just a real line. And I have here a function f defined on j and another function phi. Oh, thank you. Another function phi going from I to j. And the point of the change of variables formula was that instead of integrating f over j, I wanted to integrate this composition function over I. Quite possibly you do this because maybe the composition function is nicer or whatever. Or maybe it's the other way around. You're changing the variables. So this is the composition function. But we said that there is a cost of changing the variables. It comes from this phi distorting, just made it in time, distorting the sizes of the pixels, right? So underneath integration, there's always some sort of pixelation. And when you go from here to there, depending on which way you're using this phi, quite possibly the sizes of these pixels are going to change a little bit. And so that is this cost of changing the variable. And it's this pesky factor that always shows up, almost always, let's say. And so I cannot just say that the integral of f over j is equal to the integral of f composed with phi. But if you have something here, then it's correct. And so this something was the absolute value of the derivative. Okay? And so f is Riemann integrable on j, and phi is a C1 diffeomorphism from I to j. That is to say, phi is continuously differentiable. It is differentiable, and furthermore, its derivative is continuous. And its inverse exists, and it too is continuously differentiable. It's a diffeomorphism. In other words, it preserves the differentiable structure. then I have the following formula. The integral of f with dummy variable u is the integral of f composed with phi times phi prime in absolute value dt. That was the statement. And this right here is the distortion constant, distortion factor, if you want. Distortion caused by phi. Okay. How many of you have heard of this thing called the integration relative to the, let's say, polar coordinates? Right, so this is like a multivariable thing, but maybe I should mention it, because this formula holds in multivariable as well. This derivative is not a number anymore, but it's something else. It's, well, it's still, here you still put a number, but it's not just a derivative. It's what is called a determinant. So how many of you have taken linear algebra? Okay, pretty much all of you. So, example, polar coordinates. In 2D calculus, let's say. So how do you do this? So now your change of variables goes from the r theta space to xy space, right? So goes from r theta to xy, where x is r cosine theta, and y is r sine theta. So these are supposed to be sort of rectilinear coordinates. The point is that in the xy domain, if you have a circular shape, if you have a circular shape in the xy domain, if you switch over to the r theta domain, in the r theta domain becomes rectangular, but this guy does exactly the distortion you need. So what I'm trying to say is something like this, perhaps. So if this is xy, let's say you're trying to integrate something over the unit disk, right? So you can write x squared plus y squared is less than or equal to 1. Let's say this is this domain, but it's not as convenient to integrate this. So you do this change of variables. I say this is 1. So x squared plus y squared is like this. Instead, you switch over to the r theta domain. Now the radius is bounded by 1, and theta is from 0 to 2 pi, right? So you see, this disk becomes a rectangle in the r theta domain. And so what you want to do is, instead of integrating some function over this guy, you want to integrate the composition over the rectangle. But there's a distortion. There's going to be a distortion like this. What is the distortion? Do you remember? So what do I want? We don't know what it means for a function to be Riemann integrable, but maybe whatever that means, certainly continuous functions should be Riemann integrable. Okay, so for now, let's just imagine that lowercase f is continuous, defined on this unit disk. And I would like to make sense of this guy. Let me call this S, and this guy R. I want to integrate f over S dx dy. Because I have two variables now, I cannot just put dx here. You're gonna spend a lot of time making sense of this in multivariable calculus, but still. So I want to make sense of this, but instead of integrating it like this, I want to integrate the composition, which now takes r and theta. Phi of r comma theta is r cosine theta and r sine theta here. There's a distortion coefficient, just like here. Now, instead of just having the lengths being distorted, you're distorting the areas. But still, this is going to be a number, because otherwise you wouldn't be able to multiply this by this. And then dr d theta. So there's a number that should go there. Or there's a function, let's say. Do you remember? In multivariable calculus, they just tell you that this is how it is. Typically, maybe they sort of give you some intuition. But the point is that the number that should go there turns out to be r. It's a function after all, because you're integrating relative to r. And you have to put that there, okay? So it's reasonable, I hope, to expect that if you're taking this box and sort of distorting it to turn into this shape, something has to give, okay? Something has to change. And that something should be proportional to the radius, right? So because, maybe I can be a little bit more explicit here. Let's try to understand this phi. So for instance, this is 1. And as I'm traversing from 0 to 2 pi on this right edge of the rectangle, what happens is that I'm traversing the perimeter of the disk, right? So this turns into this. Okay. And for instance, if I were to fix the radius, or yeah, if I were to fix the, angle, let's say pi here, and move this way, the angle would be fixed as pi, but I'm increasing the radius. So this line turns into this line. Okay? So you're sort of taking this thing and you're sort of like wrapping it around in a sense. And things get distorted. And the reason why this happens, so how do you compute this r? I'm saying this r is basically whatever the analog of this is for phi this multivariable function. And it turns out what you do is the following. In multivariable calculus, if you have a function that depends on two values and gives back two values as well, let me just erase all this stuff. So let me be a little bit more explicit here. Phi of r comma theta is r cosine theta comma r sine theta. Now you have a bunch of partial derivatives. You have two component functions. These are single variable. I have two single variable functions. Both of them depend on both r and theta. Somehow I need to incorporate everything. And so what you do is you look at all the partial derivatives. Then you put them in a matrix. You look at, let's call this phi1, first component of phi. This is the second component of phi. Then it turns out that phi prime is all the partials of all the components. And then like this. Okay. And so for instance, this guy, because phi1 is r times cosine theta, it's partial relative to r. Remember, you just take the other variable to be constant. So if I pretend that theta is a constant, the derivative of this relative to r is just cosine. And then the same function, if I were to think of r as the constant and theta as the variable, because I'm trying to take the partial relative to the other variable, then becomes minus r sine theta. And then similar things happen here, right? So this becomes sine theta, this becomes plus r cosine theta. Okay. This is a 2 by 2 matrix. How do I get the number out of a square matrix? The first thing you should think, I mean, if you take sort of linear algebra, that's the thing that they teach you. So that whenever you have a square matrix, if you want to get the number out of it, you just take the determinant. And the determinant of a square matrix, at least 2 by 2 square matrix, is this by this minus this by this, which gives you r times sine squared plus cosine squared. But I know that sine squared plus cosine squared is 1, which means that the determinant of this guy, so determinant of this is just r, which is this number. Okay, and the idea is, of course, just like in single variable, phi prime is the linear approximation, right? This was a stronger interpretation. In multivariable, the derivative, again, is a linear approximation. In higher derivatives, the linear object is more complicated than a line. It's sort of like a plane or something. That's why, so this linear approximation looks a lot different, like a lot more complicated. But it's the same idea. Okay, so any questions about this? This is not super important. I just wanted to sort of relate the single variable version to the multivariable version. This shows up everywhere, and it's like, when you're first learning this stuff, it's very common to forget this r, but you know, it has to be there due to foundational reasons. Something has to give. Okay, so, and there are, of course, many other sort of situations, and why you would want to go over to the polar coordinates has to do with the domain, the shape of the domain. You have sort of like a sense that, oh, you know, if I were to change the variables, possibly integrals would be easier, but that also depends on the function f, for instance. And of course, in multivariable calculus, you learn all these different tricks that tell you, oh, for this integral, do this change of variables and so on. That's a different matter. In abstract, these things are not emphasized. Okay, so this was a statement. And last Tuesday, I did show you that this guy on the right-hand side that I'm integrating is indeed integrable. I'm not going to do that again. So we had shown that phi, f composed with phi is Riemann integrable on I, which implies by one of these exercises that this function is Riemann integrable. Hence, by the exercise, f composed with phi multiplied by the phi prime in absolute value itself is Riemann integrable. Which means that the right-hand side makes sense, okay? But still, at this point, there is no reason why the left-hand side equals to the right-hand side, which means that we have to do that. We have to show that indeed the numbers are equal. Thus, it suffices to show that this is equal to this. Okay. Well, the way I thought about proving this was by just looking at sort of like a Riemann sum. And then from Riemann sums, I can switch over to the lower and upper Darboux sums and so on, do something. So, let me let P, curly P, to be an interval partition of I. Okay. Well, if P is an interval partition of I, then the image partition, phi of P, which I obtained by applying phi to each of the pixels of P, and so this is phi of P, where P varies in curly P, is an image interval partition of J. Furthermore, if I had a sampling function for P, I could compose that sampling function with phi to get a sampling function for the image partition. Also, if S is a sampling function for curly P, then phi composed with S is a sampling function for the image partition, for any sampling function. Okay. So what do we need to do? Given any P, given any pixel, I can apply the mean value theorem to phi restricted to this pixel P. Gives that the length of the image of the pixel P divided by the length of the pixel P is phi prime applied, or at some point, S gives for some S of P in P. So I'm just looking at the endpoints. This was sort of like the trick that we used in the proof that F composed with phi is Riemann integrable also. It's the same trick, a mean value theorem. Okay. But then, this is a sampling function, this S, because I can apply this mean value theorem to each pixel of P. And so I have a sampling function. And so, then what I have is this. Yes, what I'm going to do is I'm going to look at the Riemann sum of F relative to this guy, to the image partition, and the push forward, so to speak, sampling function. This is by definition the sum over all pixels in P of F of the value of this right, times the length of this guy. Okay. So I can replace this numerator here, which I see over there as well, by length of P times the distortion. And instead of writing this like this, I can compose F with phi and evaluate it at S of P. So this becomes this, evaluated at S of p times length of p times this, which I can write like this. But then you see, this is nothing but the Riemann sum of this product function relative to the partition curly p and the sampling function s. So you see in this sort of pairing, if you want, between functions and partitions with sampling functions, either you can pre-compose the function with some change of variables, or you can post-compose the change of variables function. Okay, so either you put the phi here or there. Okay, either it's here or it's here. But then this gives you sort of like a comparison between this guy and this guy, and then you can switch over to lower and upper Darboux sums, blah, blah, blah. Let me not finish this. I'm going to leave it to you as an exercise. This shows that the integrals have to be the same. Okay. So either you're going to take a partition here, either you're going to take a partition here and push it forward, or if you have a function here, you're going to pre-compose it. And it turns out that at least at the level of Riemann sums, finite Riemann sums, the equality holds. And it turns out that when you take the limit 2 over partitions, for instance, the same equality holds still. That's the main idea. Okay. Any questions about this? Lots of fun stuff. So if you've taken linear algebra, for instance, you probably heard of something called the transpose of a matrix. That's sort of like a similar thing. So this operation on partitions together with sampling functions, post-composing, is a transpose of pre-composing the function and multiplying it by the distortion factor. They're sort of like the transposes of each other. Okay, so that's that. Let's talk about improper integrals. I'm not going to discuss the formalism behind it too much. The main point, though, is that so far we only talked about integrating functions whose graphs fit into a bounded rectangle. Right? We looked at functions defined on compact intervals, closed and bounded intervals, that are also bounded. Which means that if I were to draw the graph of the function I'm trying to integrate, I required to begin with that that graph fits into a bounded rectangle. But it turns out that in applications, physicists, engineers, and so on, want to be able to integrate functions that are more general than this. And so this is the context of improper integrals. Improper Riemann integrals. And so now I'm going to generalize the notation. I'm going to take an arbitrary interval. Let's say I be an interval, be a subinterval. So it could be open on both sides, one side open, one side closed. It could be unbounded, whatever. And I'm going to have a function f defined on I. And I'm going to call it locally Riemann integrable if the restriction of it to any closed and bounded subinterval of I itself is Riemann integrable. Is locally Riemann integrable if for any compact subinterval j of I, f restricted to j is a Riemann integrable function on j. Okay. Now certainly, if I itself was a compact interval, closed and bounded interval, any Riemann integrable function on I would also be locally Riemann integrable. But you see this generalizes the situation. So let me give that as an exercise. If I is of the form lambda to rho, like this, then f on I is Riemann integrable if and on f it is locally Riemann integrable. Locally Riemann integrable. And let me denote the set of all local Riemann integrable functions R sub log of I comma R. So let me write it here. Okay. Now, once I have something like this, a locally Riemann integrable function, for instance, any continuous function or any differentiable function on I would be locally Riemann integrable. Well, of course, the next thing is to figure out what is the integral. And the way you define this integral is by taking the integral of the function on a domain on which you know how to integrate, and then taking the limit of the boundaries. I'm not going to write it down. A couple of things may go wrong. One thing that might go wrong is maybe I itself is bounded, but f is not. Okay? Maybe I is sort of like an open interval, but there's an asymptote here, something like this. Now, we were assuming so far that the function we were trying to integrate was bounded, but if it's unbounded, it might still be the case that it has finite integral. Okay? And so here's an example for this. I'm just going to look at an example. Let's look at this. Zero is open, 1 closed, so I don't have 0. And I'm going to have one parameter, let's call it alpha. Let's say it is positive. And let me let my function f to be 1 over x to the alpha. So okay. So for instance, when alpha is 1, this becomes the hyperbola. So this is 1, no matter what alpha is, f of 1 equals 1. And as I'm going, as I'm taking x to 0, there's a vertical asymptote, right? And I would like to make sense of the integral of f on I from 0 to 1. Okay? And so this is an improper integral. Then this is an improper integral because f is unbounded on 0 at 0. Maybe I should say f sub alpha to represent the dependency on the parameter. Okay, and so what is the problem here? The problem is the asymptote at 0. If I had tried to integrate f over, let's say, epsilon to 1, that would make sense because f is continuous. It's a perfectly defined, well-defined function. It's bounded, and I can integrate. And then, if possible, maybe I can take epsilon to 0 to make sense of this improper integral. So I'm going to define this to be the limit as epsilon goes to 0 of the integral from epsilon to 1 of f sub alpha. Of course, if the right-hand side makes sense. If right-hand side is defined. Okay. Now, this expression certainly is well defined. It's a finite number because f sub alpha from epsilon to 1, so you see I'm chopping off the function here, getting rid of the asymptote, and here it's a perfectly valid function. And I'm integrating over here, and I'm just going to take epsilon to 0. If that limit exists, that limit is going to be the definition of this improper integral. Okay? So what do you need to do? You need to compute this integral. Let's compute it. Substituting, I have that f sub alpha of x is nothing but 1 over x to the alpha dx. Now, can I guess an antiderivative for this guy? If I can guess an antiderivative for it, I can just evaluate the value. I can evaluate that function, that antiderivative at the endpoints, and that would be the end of it, right? But what is an antiderivative of 1 over x to the alpha?
Is the antiderivative just going to be x to the negative alpha plus 1 divided by 1 over negative alpha plus 1? Is that what you mean?
So, okay, so what your colleague is suggesting is that this guy, of course, is x to the minus alpha. And the rule is you always add 1. And the differentiation sort of takes the exponent as a multiplier, which means that you need to divide by that multiplier. So you add 1, and then you divide by 1, by this number.
Yes, that's
okay.
what I'm saying.
Yes, it's almost correct, except that I didn't tell you that if alpha is not equal to 1. What happens if alpha is 1? What is an antiderivative?
Get the natural
Exactly, right? So you have two situations. If alpha is not equal to 1, otherwise log of x. Okay? Now the function depends on the parameter. It's certainly expected that an antiderivative of it too is, it too depends on the parameter. And of course, there's also plus c here if you want, of course, but it's not going to matter because we're just going to evaluate it at the endpoints. And the fundamental theorem of calculus item 1 says that no matter what antiderivative you use, insofar as you use the same antiderivative, it's not going to matter. You can take any antiderivative of the function, as long as it exists, and evaluate it at the endpoints and look at the difference. That difference is going to be the integral. And so this is this is on the side. So this just means that maybe I should call this something. Let me call this g sub alpha. And I'm doing a weird thing here. It's a piecewise defined function, but the pieces of the function depend on the parameter, not on x. But still, this is a valid thing to do. So this is nothing but g sub alpha evaluated at 1 minus g sub alpha evaluated at epsilon. Okay. Writing this down explicitly gives me the following. So this is 1 minus epsilon to the minus alpha plus 1 divided by minus alpha plus 1 if alpha is not equal to 1. If alpha is equal to 1, then this is log of 1 is 0, sorry, minus log of epsilon. Okay, so we were able to compute this integral. This is a definite, proper Riemann integral. Depending on epsilon and alpha, I have the values. Any questions about this? Now the point is, of course, in order to make sense of the improper integral, I'm going to have to take the limit of that as epsilon goes to 0. But you see, depending on the cases, I have different outcomes. Let me delete this. I'll continue here. Now, as epsilon goes to 0, let's say that we're in this situation. I know that log goes to negative infinity, which means that this goes to positive infinity. So if alpha is 1, then this improper integral over here blows up. It gives you infinity. Area underneath is infinity. However, you see, maybe I can handle this. And so what I want is, I want this guy to converge to a finite number as epsilon goes to 0. So I want this to decay to 0. This guy has to go to 0. For which values of alpha does that go to 0 as epsilon goes to 0? Yeah. No, but like, so I think you're close. If the exponent were a positive number, right, the asymptote would go to 0 as epsilon goes to 0, which means that I need that minus alpha plus 1, a positive number. In other words, if alpha is less than 1, is this correct? Right, exactly, okay. Yes, because if this exponent were negative, then this value would blow up as epsilon goes to 0. I want it to go to 0, which means that I need the exponent to be a positive number, which means that alpha has to be strictly less than 1. And it turns out that otherwise, it's going to blow up, which means that if alpha is greater than or equal to 1, this blows up. Otherwise, in the limit, this goes to 0, which means that the integral is 1 over minus alpha plus 1. Let me just check. Yes. So this is interesting, right? Because if alpha, for instance, were 1/2, 0.5, then I have an asymptote, okay, goes to infinity, but the area underneath converges to a finite number. That's an interesting situation. Okay. And so you would say that for alpha between 0 and 1, the improper integral of f sub alpha from 0 to 1 exists and is equal to this number. Otherwise, it's infinity. Maybe it exists, maybe it doesn't, depending on your preferences. Okay. Any questions about this? There are many sort of integrals like this that show up. Yeah.
This is strikingly similar to that one infinite series, like x plus x
Yeah.
equals x cubed, as that goes on forever.
Yeah.
I suppose that's why we're doing this.
Yeah. So another exercise would be to compute the same thing, but for f defined from 1 to infinity. So exercise, and this will be the last thing I'm going to say. Same thing. Then compute the integral from 1 to infinity. And how are you going to do this? You're going to compute the integral from 1 to some number m, and then you're going to take the limit as m goes to infinity. See if you can sort of come up with the computation like this. It's very similar. Okay? Pretty nice. Okay, so that's it for today. Tomorrow we're going to do some interesting stuff. I would like to discuss these weak derivatives, and then we're going to be on our way to compute and talk about series. Thank you. Okay, let's start. Good morning. So today is our last class on integration theory. We're going to do something slightly more advanced. It's an interesting situation. And then tomorrow we're going to start discussing the final topic, major topic of this class, which are infinite series. But I thought it would be nice to sort of discuss this, because when I first learned about this, and typically you learn about differentiating non-differentiable functions, perhaps in a class of differential equations. In differential equations, typically you're given a function, f, and you want to solve for g. Right, so a typical differential equation, at least an ordinary differential equation, is of this form. So given an f, find a g such that this happens. And of course, this is important for math, pure math purposes. It's also important for modeling purposes. A lot of applied people are interested in these kind of things, because it turns out that many natural phenomena, at least approximately, are modeled by equations of this form. Somehow, the nature gives you an f, and your job is to find one g, or many, if possible, all g's, such that this happens. And sometimes, so approaching this from the single variable point of view, this already gives certain restrictions on what type of f you can have. For instance, it has to have the intermediate value property for this to be solvable and stuff like that. But you might have more complicated functions, f, and maybe it's not clear immediately if you can, in fact, solve this type of an equation. And further, maybe you're given a function that has no solution, so such that this equation has no solution g, like we looked at before, right? So we had an example of f like this. Then we said that this has no solution, and then we started interpreting this equation in a weaker sense. And we came up with this idea. This was sort of the lead up to the fundamental theorem of calculus. We, for instance, defined f of x to be, let's say, from gamma to x f of t dt. For this function, we were able to do this. And even though this is not necessarily differentiable everywhere, it is differentiable at most points. And when it is differentiable, its derivative is this guy. OK. And so it turns out that this happens all the time. And there's a general theory behind this whole thing, which is a theory of what is called distributions or generalized functions. The theory of distributions or generalized functions. Okay. So let's say that I have a function f. This was sort of the background. Let's say that I have a function f that I'm trying to differentiate. I want to come up with f prime. F want f prime. Of course, the standard method is to look at the limit that defines the derivative at any point, and you sort of vary the base point, and that gives you the f prime if possible. But maybe you know that you cannot do this for whatever reason. You know that your function is not necessarily differentiable in the standard sense that we discussed. So somehow you need to interpret this f prime or prime operation, differentiation operation, in a weaker sense. Well, one way of doing this is to look at integration by parts. For any sufficiently differentiable function, right? So let me call it phi, sufficiently differentiable, maybe C1. C1 is not necessary, of course. We looked into the integration by parts formula. What is sufficient is that my function is differentiable and its derivative is Riemann integrable. But what I can do is, if this is my unknown, it would need to fit into this equation. Right, so let's say from alpha to beta, and then from alpha to beta minus phi prime f from alpha to beta. This is integration by parts. Now, if f prime is not well defined, obviously this doesn't make any sense, right? But the key idea here is that even though quite possibly f prime doesn't make sense, which means that the left-hand side doesn't make sense, the right-hand side makes perfect sense. Let's say for f Riemann integrable. And so at this point, there are two things you can say. Either you can say, this doesn't make sense, you pack your things and go away. Or the fact that one side of the equation is undefined, you can use and define it to be the other side. Okay, this is like a postmodern way of doing things, but postmodernism in math has been happening for a very long time, at least 200 years, I think. This is like a 200-year-old idea, actually. And so there is like a bunch of there's a bunch of theory behind this. It's a whole field. And typically what people would want to do is they would want to use something like the integration by parts formula to make sense of f prime, even though perhaps the standard f prime doesn't make sense, and then perhaps they can upgrade it. Right? So we saw this idea before too. If you're trying to find something, find a thing in a weaker sense, then try to upgrade that sense, right? So for instance, if you have a sequence of functions, and if you want to find the uniform limit of it, first you find the pointwise limit of it, and then you see if you can upgrade that pointwise limit to a uniform limit. Same idea. Now, I'm not going to sort of discuss all the sort of nitty-gritty details. I just want to stick to some examples. Let's look at this famous function. It is called the ReLU. How many of you have heard of this? Yeah, this is a famous function. It's short for rectified linear unit. It's one of the most common so-called activation functions that people use in machine learning. And it is defined like this. Let's say my interval is from -1 to 1. And this is defined like so. Take an x, send it to x. If x is non-negative and 0 otherwise. So its graph looks like this. The point is that this is an activation function, and if the signal coming in is negative, this function just kills it. Otherwise, it doesn't do anything to it. So this is like non-activated neuron. That's sort of the idea. In here, you sort of let it pass. That's my function f. Okay. Certainly, this function is not differentiable. It's not differentiable in particular at 0, and that's the only point at which it is not differentiable. Right? F is differentiable everywhere except at 0. Certainly it is continuous, and if I want, I can look at the tangent lines, right? If x were a negative value, the tangent line would be the horizontal line. If x were positive, the tangent line would be the diagonal. At the origin, there is no tangent line. There is no line that is tangent to f at 0, in the sense that we saw in the midterm in the previous problem set and so on. Okay. But what I can say is that I can draw whenever the derivative exists. Okay. If you forget about the origin, here, when x is negative, f is constant, so its derivative has to be 0. Let me just draw it like this. And if x is positive, well, this is the diagonal line. Its derivative has to be constant. It has to be 1. This is yet another famous function, let's say. Oh, almost. This is basically going toward what is called the Heaviside unit step function. And so what I need to do is I need to add this point as well. So this, let me call it h. This is the Heaviside unit step function. You should think of this as an on-off switch, right? As x switches, goes from negative to positive, it turns on to 1 and it stays at 1. Heaviside unit step. My claim is that h is, in a weak sense, the derivative of f. Certainly, this cannot be the standard derivative because it doesn't have the intermediate value property. It has a jump discontinuity. But perhaps in this weak sense, I can handle this. Okay? Now, I want to use integration by parts. So what I need to do is, I need to sort of take whatever function, maybe h prime, which I know doesn't exist, but I'm going to pretend that it exists. I'm going to define it so that integration by parts work. But I need to pair that h prime with some nice function phi so that I can do integration by parts and sort of transfer the supposed derivative on h to the function next to it. Okay? So my claim is h prime equals f in the weak sense. Well, in a weak sense. There are multiple weak senses, but okay, let's see what's like this. So I'm going to have to pair this h prime with some nice function. My nice function is going to be, these are what are called test functions. I want my test functions to be infinitely differentiable to begin with, because otherwise I wouldn't be able to perhaps transfer the derivative, a legit derivative of h, to this other function, because I would like to be able to differentiate it multiple times. And furthermore, I want my test function to have 0 at the boundary. So that's a definition. A test function on I, this interval, is a phi c infinity, infinitely differentiable. And let's say that for any derivative, well, I guess we're not going to need it. Let's say that at the endpoints, it is 0. So in differential equations, you would call this vanishing boundary conditions. And maybe in a second, I can mention why this is sort of like a natural thing to look into. Then for any, so let phi be a test function h prime, if it exists, has to satisfy the integration by parts formula by definition. That's the definition of weak derivatives. In the weak sense, exists if integration by parts work. Work with phi. That is to say, integral from minus to 1, phi of t, h prime of t, dt. This has to be phi of t, h of t, where t is evaluated from -1 to 1. Minus -1 to 1 integral phi prime of t h of t dt. Okay, so I don't know what this is, but I'm saying that whatever this is, it has to fit into the integration by parts. The point of doing this is that the right-hand side makes sense, so I can define the left-hand side as the right-hand side. So the left-hand side is defined as the right-hand side. But you see, this is the benefit of choosing vanishing boundary conditions, because I know that phi of 1, no matter what h is going to be 0, minus phi of -1, 2 is going to be 0, so that this part is going to be 0. It's going to vanish. Okay, so this is 0. Now I need to figure that out. Okay. So continuing from here, but h of t is 0 for t negative. So this integral I can just rewrite as this. 0 to 1 phi prime dt. I have a minus sign, you see, because I used integration by parts here. This minus is important. Now what is the next step? There's a final step here. How can I sort of write this integral in a much more pleasant fashion?
It's phi prime in there, so the integral and the derivative would sort of cancel out.
So what is this?
I think it would just be phi of 1. Actually phi of 0.
Exactly. Right. So you have a minus, and then you evaluate this at the endpoints by the first fundamental theorem. But then I assumed that phi of 1 is 0. Vanishing boundary conditions. So this is just phi of 0. Okay, this is the proof of something that I was going to do. This is not the proof of this. It should have been the other way around. So we computed the weak derivative in a sense, but I computed actually this is delta. So this is written also as -1 to 1 phi of t delta of t dt. Okay. Sorry, I wanted to differentiate f in the weak sense to get h. So let's do that first. I'm just going to do the same thing. F prime equals h in the weak sense. And so I need to start with this guy again. I take a test function. -1 to 1 phi f prime equals, again, by integration by parts, I'm going to have phi times f from -1 to 1 minus integral from -1 to 1 phi prime f. Okay. Phi prime f. Okay. Dt. This is 0. again by the vanishing conditions, vanishing boundary conditions here. F had this form, remember. This was F. So I can split this integral to one integral from -1 to 0. That's going to be 0 because F is 0 there. And then another integral from 0 to 1, where F is going to be just x, or t in this situation. So this is just going to be minus 0 to 1 phi prime of t times t dt. I can apply by parts again to this, right? So I can transform, I can sort of send the derivative to this side. So this would be phi of t times t, where t varies from 0 to 1, minus, right, 0 to 1 phi of t dt. Nice. I use by parts again. Again, at 1, phi of t is 0 by the vanishing boundary conditions. At t equals 0, this is 0, so this is again 0. I don't have it. So this is 0. But then I have two minuses. And so this is just 0 to 1 phi of t dt, which of course is the same thing as integrating phi against the unit step function. You see, integrating f prime against this test function is the same thing as integrating the same test function against the unit step function. So this was my my f, my h was this. And this is true for any differentiable phi whatsoever, any test function phi. So I'm trying to test, and I'm trying to test my function f prime, for instance, or whatever this is. It's not in general going to be a function like we discussed before, but in any event, insofar as that this derivative exists, for any phi, this integral has to be the same thing as this. That is what it means for f prime in the weak sense to be equal to h. In the weak sense, does this kind of make sense? This is like a very different way of thinking about differentiation, and in particular functions themselves. Okay. And you see, I did the same thing here. I differentiated h instead of f. And when I differentiated it, ultimately I got delta. And so this is a bizarre statement, but this integral literally means phi of 0. This delta is a bizarre thing, okay? Now, this delta is called the Dirac delta function, but it's not a function, okay? This is called Dirac delta. Function. But it's not a function. It is what is called a generalized function, or it's a distribution. Okay. Now, let me mention something about this. Why would you how could you sort of figure out that integration by parts was the thing that you could use to differentiate things, even though the derivatives of these things are not well defined in the standard sense? Well, it's all about understanding what it means to integrate a function against another function. Okay. So now we're going to try to sort of adjust our understanding of functions so that it is closer to experimentation. And then in a second, I would like to mention a couple things about this delta function. From a more sort of realistic point of view, you have a phenomenon, a physical phenomenon, and you model it. You want to do math with it to predict, right? That's the main purpose of math for a lot of people. It has predictive power. You get to just predict the future, which means that if you can predict it better than other people, you can beat them, right? Unfortunate, but this is one of the major reasons why math is this developed. In this pure sense, if I have a function, I can figure out each of its values, right? So I can plug in one input value, and it gives me f of x. But in reality, even if you could model your phenomenon by a function, let's say it's a temperature distribution or a density, whatever, well, to get a number out of this function, you're not going to be able to plug in one specific value. I mean, you can, and it's going to give you something, but there is no reason for this f of x. You fed the input x into f, and it gave you this number. There is no reason for this number to have any connection with the original thing you were trying to model. And second of all, it's even dubious how you could sort of plug in a certain input value to a function. In reality, even if you have a distribution like this, you have a function like this, what you really do is you have sort of like a gadget, you have some, I don't know, some sensor or whatever. What you're really doing is that you're taking the average of it, in a sense. The best thing you can do is, instead of looking at f, you multiply it by some function, a test function, that is localized near the input value that you're really interested in. You cannot really plug in one thing, but what you can do is, if this is the sort of theoretical value, theoretical input you're interested in, what you can do is you can look at a test function like this. It has a bump, which with a climax exactly at this value that you're interested in. Then you're really seeing this value. This average is basically what a sensor would give you. Well, maybe I should say this is x star. So this would be basically this. Okay? So you would have some noise. You wouldn't be able to plug in x star into f to get the exact value, but you would be able to get some average, and you could skew the average so that the value that you get is sort of like localized to the point that you're interested in, to the input that you're interested in. Okay? And really, plugging in one value into one function is sort of like an extreme case of it. If you could take bump functions. So let's say that this is the input that you're interested in. If you could take bump functions like so, so if you could come up with bump functions and take average in this sense of f for bump functions that are arbitrarily large in amplitude, let's say, in the limit, you would get f of x star. And that's really what this delta is. So let me write it like this. Now, at this point, this delta of x minus x star is not a function anymore. It's a generalized function. But whatever it is, this integral has to equal to f of x star. So this is a different way of thinking about things, because all of your experience, all your experience in math, so in all the classes that you've taken, if you have a function of x, let's say, you are able to plug in a certain value for x to get the output. But that's not how actual math works, or that's how it works in more sort of realistic situations. All you can do is take an average. And this, integrating against a nice function, is basically the best thing you can do. Okay? And so that's why it is reasonable to look at expressions of this form. Okay? So if you want to figure out the value of x, the value of f at x star, you look at a bump function whose climax is near x star. You multiply this by this so that you get rid of everything else. You take the average. That gives you an approximate value for f of x star. If you want to figure out the value of f at, let's say, y star, then you do a similar thing, but now your bump function has to be here. Okay? Any questions so far? Okay. Okay, I told you that I was going to say something about this delta function, but I'm going to leave it to you to think about this. It takes a while. So typically in sort of differential equations classes, even for engineers, at some point we start talking about delta functions. We say a couple words about how it's not an actual function and stuff like that, but it sounds mysterious, and it is a little bit mysterious, but once you learn sort of the background a little bit more, everything is perfectly rigorous. Now, 200 years ago, when people started using this, it was more dubious, but by this point, everything is sort of like formalized, at least for these type of things. What I want to do is, I want to connect this back to the fundamental theorem of calculus, because it's an interesting thing that happens. Specifically, I would like to focus on fundamental theorem of calculus 2. So claim. So I have an I, an interval from lambda to rho. It's a closed and bounded interval. Let me let f be a Riemann integrable function. Let me let gamma be a point in I. And let me define f sub gamma, this cocycle, this family of cocycles. Right? So this was a function defined like so. it's a function on I, it takes x to the signed integral from gamma to x of f. Fundamental theorem of calculus 2 says, one part of it was that this is Lipschitz continuous, this f sub gamma. And furthermore, at any point where lowercase f is continuous, uppercase f is differentiable. Okay. My claim is that the weak derivative of this guy is lowercase f. Even when I don't assume that lowercase f is continuous, I can differentiate uppercase f, and that derivative is going to be lowercase f. So fundamental theorem in the weak sense still holds, but it has to be in the weak sense, of course. So something has to give. That is to say, so by definition, for any C infinity function, infinitely differentiable function on I with endpoints 0, one has this. So I'm pretending that I can use the integration by parts, right? So let me just write it like this. Phi. So lambda to rho, phi of t, phi of x, f sub gamma of x prime dt equals and here again the left hand side is defined so that integration by parts works, which means that this left hand side is actually defined to be this minus lambda to rho phi prime of x f sub gamma of x dx. So this doesn't make sense, but this does. So I'm defining this to be this. And so the statement of the claim is that this integral is equal to this integral. That's what it means for f prime to be weakly differentiable and its weak derivative being equal to lowercase f. Okay. Oh, I should also mention, of course, because I'm defining these weak derivatives through integration by parts, any strong derivative, any classical derivative, is going to be a weak derivative. Right? So proof of claim. I'm not going to continue with the proof if I can finish it today. But at the very least, I would like to give you an idea. So I take a test function, a phi like this. I start with this. This is defined like this. And for simplicity, let me choose gamma to be lambda. This works for any gamma, but it's going to be easier. Proof for gamma equals lambda. So I'm taking the integral starting from the left end point. And arbitrary gamma case I'm going to leave to you. It's a nice exercise. So lambda to rho phi of x capital F prime of x. This capital F is just f sub lambda. I don't want to keep writing it. This is by definition, minus integral from lambda to rho, phi prime of x f of x dx. What can I do now? Somehow I need to sort of do something. Well, ultimately that's what we did here. But somehow I want to go back to lowercase f, right? So in this expression, ultimately, I want this to be the same thing as integral of phi times lowercase f. So I need to get lowercase f here. How can I get lowercase f? Even simpler, I can just write down the definition of capital F. Now things are getting messier. But it's going to work. You see, this is a single variable calculus statement, but somehow we're getting double integrals in it. I just wrote down the definition of capital F of x. It's an integral after all, and I have an iterated integral. Now, this guy is constant in t, which means that this I can put inside this inner integral. You're going to learn these things more if you take the SQL class, but this I can do. I have an iterated integrals like this, iterated integrals. What can I do now? There's pretty much only one trick when you have iterated integrals. When you get stuck, what you do is you flip the order, right? Then things work somehow. Now I need to be careful though. So I'm thinking of the xt domain, right? And x varies from, let's say, so here's lambda to rho. X varies between lambda to rho, and then t varies from lambda to x, which means that the domain of integration of this iterated integral is this rectangle. It's a triangle, sorry. This iterated integral first varies x and varies then t as a function of x. So it's doing this. But the point of doing this is that instead of integrating it this way, I can integrate it using horizontal slices. Now let's assume that we can do this. This is something that needs to be proven, and I think they're going to prove it in the second class if you take it. This is what is called the Fubini theorem. Fubini says that you can change this, the order of integration, at least in this case. So this is what is called Fubini. Now, outside I want to have, so let me first write it like this. So it's going to be like so. And then first I want dx and then dt. T is going to vary from lambda to rho. So the outer integral is going to go from lambda to rho again. But now I want to vary x as a function of t. You see now x is going to vary from t to rho. If this is confusing, it's not a major issue because this is like a multivariable thing. Let me delete this. But now I can do the same trick, you see. For this inner integral, which is relative, which is, the independent variable for the inner integral is x, which means that this is a constant in x, which means that I can take this number outside the inner integral. Is equal to this. What is the next step? I have the integral of a derivative. So what is this?
So it's just dp of x evaluated at rho.
Okay. So again, I'm using the first fundamental theorem. This is phi of rho minus phi of t, f of t, dt, which I realize I forgot a minus. You see, there was a minus here, there's a minus here, there's a minus here, there's a minus here. Phi is a test function. This is 0. I have two minuses. They cancel out. And I have this. Isn't this beautiful? It just works. I was testing capital F prime against this lowercase phi, did some stuff, and I realized that detecting values of capital F prime is the same thing as detecting values of lowercase f. That's what it means for these two things to be the same in the weak sense. Okay, and that's the end of the proof. Now do the same thing for an arbitrary gamma. This domain is going to be slightly weirder, but it still works. It just works, okay? And this is one of my favorite things. I don't do research using this stuff, but it's still very nice, I think. Anyway, I hope you enjoyed this. This was sort of like slightly different than what they usually do, but we're done with integration, at least for now. And tomorrow we're going to start talking about infinite series. Thank you. Okay, let's start. Good morning. So today we're transitioning to the final topic of this class, which is infinite sums. In other words, series. So we're going to have initially things like this. Say 0 to infinity, let's say 1 over n factorial. We would like to be able to say something about whether or not this makes sense. And if this sum, this infinite sum does make sense, what is this expression? And then once we discuss this numerical series, at the same time we're going to be discussing, or eventually we're going to be discussing similar things where the things that you're adding in fact themselves are functions. We would like to switch perhaps from this to something like this, where now x is a variable. If possible, we would like to be able to make sense of this expression at least for some x values. And furthermore, if possible, we would like to be able to figure out if we can treat this guy as a function of x itself. Right? How many of you have seen this before? This is the exponential function, right? So, and this indeed adds up to a finite number, which is the number E, of course. So we're going to sort of discuss the foundations of this. We're going to look at certain tests that you can use to determine whether or not a given series converges. But before that, I wanted to discuss what I'm calling the discrete fundamental theorem of calculus. Because this transition from continuous time, where you have functions, continuous functions, differentiable functions, whatever, but we're always thinking of the function to be taking continuous variables, any real values, as inputs. And I would like to discuss some version of the fundamental theorem of calculus, where instead of having arbitrary real numbers as inputs, just discrete values. In other words, I would like to be able to do some calculus with sequences. Okay? And it's going to turn out that we can come up with a fundamental theorem of calculus 1 and 2, for sequences. And it's going to be a lot easier compared to the fundamental theorem of calculus for functions with real variables. But I wanted to sort of keep it a little bit more abstract so that it's somehow compensated. So instead of just starting with a sequence or sequences in some arbitrary set, which we were doing so far, I want to be able to add things. Okay, it turns out that the fundamental theorem requires something like that. And so that's sort of the idea behind the vector space. How many of you have heard of this term, vector space? Okay, some of you. Vector space means you have a set, you have an addition, and you have what is called scalar multiplication. We've already seen a couple of examples of this. So let me just say a set with addition and scalar multiplication. Here are some examples. I'm not going to write the definition of it. Reals, of course, itself is a vector space. You can add and multiply. X could be R. Some set of functions taking real values. Let's say set of all real valued functions on an interval, because you can add two functions and you can scalar multiply them. So you take a function, you can take a number and multiply those two, and that gives you another function. Differentiable functions, or C1 functions, or CR functions, R times differentiable functions, is a vector space, because if you have two functions that are differentiable, you can add them up, and that sum too is going to be differentiable. And if you have a function that is differentiable, you can multiply it by some number, and that's still going to be differentiable. And likewise, for instance, Riemann integrable functions, all that stuff. All these sets of functions that I was writing for a while throughout this class are examples of vector spaces. They have more structure in general, but for the fundamental theorem of calculus, vector space structure is going to be sufficient. And in fact, all we need really is addition and subtraction. So maybe C0, CR, R times continuously differentiable functions, infinitely many times continuously differentiable functions, Riemann integrable functions, bounded functions, whatever. Throughout the class, we define so many spaces or sets of functions, pretty much all of them, insofar as they are made up of functions taking values in R, they turn out to be a vector space. Okay? So all I'm going to say, what I'm going to say now, is going to apply to all of these. Okay. And let me denote by S of x the set of all biinfinite sequences. Instead of looking at all sequences from, let's say, 0 to infinity, I'm going to look at negative infinity. I'm going to look at sequences that are defined for negative infinity as well. That's going to just make things easier to write down. So curly S of x is going to be the set of all functions from the integers into x. Set of all, this is sometimes what is called biinfinite sequences, because it goes to positive infinity and negative infinity. Infinite sequences on x. Now, from a more applied point of view, of course, I would like to imagine this S of x to be the set of all discrete time signals, where my outputs are in x. So maybe I should write that as well. Because this is also something that people, for instance, doing signal processing use. Discrete time signals. In x. Okay. Now, I would like to be able to talk about differentiation of a sequence. So this is my function space, so to speak. And it kind of makes sense because thinking about functions like this that take sort of arbitrary real values is sort of like an abstraction. Like when you think about it from a more sort of experimental point of view, there is no such thing as infinite resolution. And we would like to imagine, for instance, that time is a continuous thing, but that is not an empirical statement. Because when you think about it, all, let's say, experimental gadgets have sort of like a lowest time sort of interval that it can sort of model. There's no such thing as actually sort of seeing or experimenting or observing time as a continuous thing. Of course, we have that sense, but when you really think about it, humans too are sort of mechanical machines or biochemical machines, let's say. And perception for humans are just electronic signals and stuff like that, which means that because we too are physical, there's sort of like a minimal time duration beyond which we are unable to detect anything. We still would like to imagine that time is a continuous thing, and that's why calculus was defined this way or was developed this way. But then this is sort of like a more classical approach. You see, we don't really emphasize this that much in math classes, but of course the killer app of math is physics. And most of what we were discussing so far, calculus, continuity, all this stuff, they are defined so that physics or classical physics, Newtonian physics, is relatively easy to describe. But of course, there are many other types of physics, quantum physics and other things. And so that sort of suggests that perhaps if you were to change your perception of how you should be modeling reality, then your math should change as well. Right? And so, in a sense, it does make sense then to try to do calculus with sequences. And it turns out that there are multiple ways of doing this. And I'm just going to discuss one version of this. And so let me let x bullet be a signal. I want to talk about the derivative of this. Now the inputs are integers. So I want to make sense of, so today is going to be like a philosophical class, okay? We're going to try to define things so that some sort of fundamental theorem of calculus works. For some time n, my time is discrete for sequences. I want the derivative of x at time n. Now, how can I define this? Any guesses? There are many ways of doing this, but let's sort of brainstorm a little bit. Now, I can't quite take limits here because I can't, so it's like I cannot put like n plus h and then look at the differences. So this would be sort of like one thing, right? And then I would take h to 0. If this x admitted arbitrary real inputs, this I could do. But this is a sequence, so n plus h makes sense insofar as h is an integer. So you can't quite take the limit as h goes to 0. You're just going to get 0. Okay? But you can try to do the same thing, the next best thing. You can say, okay, so here's n minus 1, n plus 1. And then this is, the height is x sub n minus 1, and then let's say this is x sub n, and then somewhere here is x sub n plus 1. Okay, so this is x sub n minus 1, x sub n plus 1. You can say, okay, so this derivative, maybe I can do this perhaps, but at the very least it should be something like rise over run. So I need to find some sort of triangle, and you can say, what is the smallest triangle with one corner at this point? Well, it's this guy. And so let me just use the rise over run for that. So you can look at x sub n plus 1 minus x sub n divided by n plus 1 minus n, which is just 1. You see? You can do that, or you can look at this guy. People do both ways, but I'm just going to choose this implementation. So I'm going to define the derivative of the sequence x at n to be nothing but x sub n minus x sub n minus 1. Very simple. No limits. Okay, because there's nothing to take the limit over, right? My input values are discrete. Any questions about this? Now, there are multiple sort of implementations of this discrete calculus business, and it has a bunch of different names. Finite calculus, business calculus, quantum calculus, whatever. There's a bunch of different names. And maybe some people would like to say, instead of using sequences, they still use real valued functions like this. And they still write this rise over run, but they don't take the limit. And they say this is the h derivative of f at x. H is a fixed, very small number. They say, oh, like due to experimentations, blah, 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 or physics, there's a smallest sort of length that I should be thinking about, which is the Planck constant, perhaps. And then they just do calculus with this rise over run expression without taking the limits. That's another implementation. Of course, the benefit of doing this is that when you take h to 0, the minimal possible length to 0, you get the classical calculus. And like if you're into physics a little bit, I don't know much about these kind of things, but as I understand, quantum physics should be so that under certain limits, you should be getting back this classical Newtonian mechanics, which is sort of like implemented here. There's different sort of like versions of this business as well, but this is sort of like the nicest, I think, least technical way of doing this. Okay, so any questions about this definition? I can certainly define this. Now, but note, in this case then, any sequence is differentiable. There's nothing that's stopping me from taking an arbitrary sequence and just looking at the sequence of differences. So any sequence is differentiable. And so, for instance, I can also say that a sequence is constant if and only if its derivative is 0. Okay? So let me give that as an example. So I would like to recover as many properties of standard calculus as I can within this discrete calculus formalism. Some things are going to be different, of course, but I would like to keep track of the analogies. So for instance, if I were to say that capital X is just the reals, and then let's say that x sub n is 1, it's a constant sequence for any n, then its derivative at any input is x sub n minus x sub n minus 1, but both of these are defined as 1. So the derivative is 0. If I have a constant sequence, the derivative is 0. And I'm going to leave it to you as an exercise to verify that even if x weren't the reals, a sequence would be constant if and only if its derivative is 0. So okay. And of course, I can keep iterating the derivative. That would be sort of analogous to higher derivatives, right? So for instance, the point of this is that, of course, everything is very formal, as you see. It's like whatever subtraction is for this capital X, I mean that subtraction. I don't quite know what exactly that is. And so, for instance, I have a sequence, let's say, a signal. Its first derivative at n is going to be x sub n minus x sub n minus 1. But then if I were to differentiate this sequence, this is a sequence in and of itself, I get another sequence that's sort of like the second derivative. So d squared x at n is d of x at n, and then plugging this in, this just says that this is dx at n minus dx at n minus 1, and then adding or opening these up once more, I have that this is x sub n minus x sub n minus 1 minus x sub n minus 1 minus x sub n minus 2, which then I can collect like so. Okay? I'm just opening up the definitions. And I can keep iterating this idea if I want. I can look at the third derivative and so on. Any questions about this so far? Okay, so any sequence is differentiable. And in fact, I can say that if dx equals y, then x is an antiderivative of y. It's also the case that any sequence has an antiderivative. Okay? So you see, things are a little bit different in the discrete situation, because there's nothing that's sort of like restricting how you're moving from this time point to this time point. See, it's like, it's very malleable in a sense. Example. Given a sequence y, solve dx equals y for x. How can I do that? Well, I'm just going to say for an arbitrary n, this means that x sub n minus x sub n minus 1 equals y sub n. Okay? And so, for instance, let's see. If I were given y sub n's, how can I solve for x sub n's? Well, perhaps I can do something like this. Okay. So for instance, so 1. Like this. I'm trying to see some sort of pattern. This goes on like this. Well, maybe let me take y0 to be a specific number. So, okay, nice. So put I'm denoting by c the 0th value of y. Then I have that x sub 0 minus x sub minus 1. Or maybe I need two values, actually. We'll see. So this is equal to y0. I should be defining x0 probably. Let's define x0. Now it works, I think. Sorry about this. So I'm just storing x0 to be this plus c. Okay, so this is analogous to that plus c in integrals that you have. Because I'm sort of, in a sense, trying to integrate y to get back x. So x1 minus x0 equals y1, which means that x1 has to be x0 plus y1, which is y1 plus c. So given any c, I can find this. And then I can plug this back in to this one. So x2 would be y2 plus x1, but I know that x1 is this, which means that this has to be like so. No, sorry, 2. And then let's do one more. And so x3 is what? y1 plus y2 plus y3 plus the same constant. And in general, of course, what is the general formula? How can I write x sub n in terms of expressions, numbers or values coming from y? What is the pattern here?
You add up all the previous values of y.
Okay. By induction, you can show this is the case. Now, what happens if n is negative? Because I'm looking at biinfinite sequences. I'm going to leave that part to you. You sort of like run the same thing, same equation in the backwards direction. Gives you a similar thing. But the point is that this is similar to saying that f prime equals g. You see, I'm trying to develop the analogy. And this is similar to saying that f is an antiderivative plus a constant. Okay. So it seems like the fact that I define this d operator like so seems to suggest that I should be defining an integration operator like this. Given a y, its integral is this guy. Which does make sense because integrals are supposed to be sort of like limits of finite sums. So in the discrete case, integrals should be just a finite sum. Okay. Any questions so far? Okay. Let's continue. So what do I need? I would like to develop this theory so that ultimately we have one analog for a fundamental theorem of calculus 1 for discrete situation, for the discrete case, and another analog for the fundamental theorem of calculus 2. Let me just remind you these two things. Now, we still haven't defined the analog of the Riemann integral to begin with. This seems like an antiderivative, but recall that Riemann integral is different than antiderivative. So once FTC-1 and FTC-2. So let's remind ourselves what these said. Forget about all the sort of like adjectives and the fine print and all that stuff. I want a formula at the very least, and the formula should be something like this, right? So from alpha to beta, integral of, let's say, f prime is f of beta minus f of alpha. This is the first fundamental theorem of calculus, the bare bones of it, right? And there's a bunch of like fine print, and like you have to sort of make sure that everything makes sense and all that stuff, but once you do, that's what it's going to say. And fundamental theorem of calculus 2 says, again, the bare bones, it says the following. If I look at this guy and then differentiate it, I get back the integrand. Okay, so fundamental theorem of calculus 1 first differentiates, then integrates. Fundamental theorem of calculus 2 first integrates, then differentiates. Okay? Again, you have to make sure that everything makes sense here, but once you do, that's what it's going to say. So I want discrete analogs of these. And at this point, let's just assume that this d operator, d as the derivative, is going to work. So the point is to define everything else so that these formulas or analogs of them make sense. Okay, so what do I need? First of all, I need to define unsigned Riemann integrals, signed Riemann integrals. Then I need to, well, that's pretty much all I need. But I need more things, of course, because for Riemann integration, we don't integrate functions over arbitrary domains because we're looking at definite integrals. So I need an analog of the closed and bounded interval I that we were using. Okay, so need. So differentiation. This is done. I defined the d. This is this d operator. We have a notion of differentiation. Now I need the analog of a nice domain, analog of a closed and bounded interval. Nice domains of integration. Maybe I should write it like this. In the classical setting, this was d by dx, for instance, and then we turned it into this discrete derivative. Nice domains of integration in the classical case was just a closed and bounded interval. So we need to turn this into something that works in our situation. What else do I need? So this nice domain of integration I'm going to use on the left-hand side. On the right-hand side, I mentioned how beta minus alpha was the boundary of the interval here. So I need a notion of boundary for nice domains. Boundary operator. So in a classical case, recall that this was a notation that I sort of mentioned. Boundary of I is rho minus lambda. And plus and minus here are orientations. So maybe I should draw it like this. Okay, so we need an analog of this boundary operation so that I can use it on the right-hand side here. Then I need an unsigned definite integral, analog of the unsigned Riemann integral, and signed Riemann integral. Okay. Integral, and then signed definite integral. In the classical setting, this was just integration over this I of f of x dx. So I need an analog of this. I didn't write it here, but this had an unsigned integration version. And we need a signed definite integral, which goes from alpha to beta. Okay, so we need an analog of this and an analog of this. And this example over here already suggests how pretty much everything else should be defined also, right? Somehow, because ultimately, this expression here, right, integral of the function with one of the endpoints as variable, if f is continuous, the second fundamental theorem says that this expression is differentiable, which means that this is going to be an antiderivative. And we found here too, this sum is something like an antiderivative, which means that somehow this should be sort of my model that should guide me through the definitions of these remaining items. And of course, the last point is that once everything is defined, they should be so that analogs, some analogs of the fundamental theorems of calculus, these two items, hold. Okay, so we're trying to define things so that the theorems work. Questions about this? Now the contents of these theorems, once we're able to define these notions, they're going to be basically straightforward. Compared to the proofs of these, they're going to be rather straightforward to prove. But you see, sometimes what is harder is to define the right thing. And so this is really the sort of the genius of Newton and Leibniz and all these people. It's not that they just realized the fundamental theorem of calculus holds. People knew that it has to hold. They just didn't know what it meant. They didn't know how to define things properly. And Riemann as well. Recall I told you that the definition of Riemann integral came pretty much 100 years after the proof of the fundamental theorem of calculus. Was Riemann sort of like was much younger. Okay. So any guesses as to how to define any one of these items? Maybe let's start with nice domains of integration.
Just some subset of the, I guess like you take an existing domain of integration in the real numbers and then intersect it with z.
Yeah, so I want consecutive integers so that I can have sums like this. So I want to say this is something like the integral over the domain from 1 to n. Okay. In a sense, this is like solving a puzzle, right? It's like you sort of like buy a box of puzzles, and like one of the things you do is you sort of first get the boundary. That's like one of the main tactics, right? And then once you have sort of like a frame, you sort of start sort of finding sort of like similar things, and you sort of like try to get the patterns, and then you try to fit them together. But ultimately, what you're trying to do is to get the big picture, and ultimately everything has to fit. So you have to have optimism again, you see? You have to have optimism that everything is going to match ultimately. And so it's going to be like this. What your colleague suggested, an interval, closed and bounded interval, now is going to be this. I'm going to use the interval notation, but I really mean, of course, n plus 1, n plus 2, all the way up to m. Okay. So that's my nice domain of integration. And its orientation should be from the smaller integer to the larger integer. And even though this is a discrete set, I'm still going to draw sort of the underlying real numbers. So this is the orientation. What is its boundary? Well, it should be this minus this. The boundary of this from n to m, oriented this way, should be this point with this orientation and this point with that orientation. So maybe I should use a different color. The point is that the arrows should be outwards. So this is sort of like your bulk, and your boundary should be outward pointing. That was the case in this situation too, remember. We had this interval from alpha to beta, and then we looked at the boundary of this, and we said that this is this, beta here, alpha this way. Any questions so far? Fairly straightforward. The next one is the unsigned definite integral. So given a sequence, I would like to define its integral, unsigned integral, over this nm, over this nice set. And I did some calculations and stuff like that. And in my opinion, okay, this is like my choice, instead of starting the summation from n, I feel like it works better if we start from n plus 1 somehow. I think the numerology works better. So, unsigned integral. So I have two integers, n and m. N is less than or equal to m. And so, again, I'm going to write it like this. This is going to be from the set of sequences to x. Okay? Now, it turns out that in this case, too, every sequence is going to be integrable. So I don't need to worry about lower Darboux sums, upper Darboux sums, Riemann sums, and taking limits over partitions, whatever. Because I have already one fixed sort of resolution that's set for my situation. And so given an x, its integral is going to be sum from n plus 1 to m. And just like in the classical situation, if I have a definition of the unsigned integral, I'm going to define the signed integral depending on, based on the unsigned integral, depending on the orientation. So this was the unsigned integral. Maybe I can, let me just delete something. I'm going to leave these two. Delete this. Okay, signed integral. Is going to be for n and m arbitrary. The integral from n to m, again, is going to be a transformation from the set of sequences to x itself. And this is like this. This integral should be the unsigned integral, like so, if n is to the left. Otherwise, it's minus the other way around. Okay. Why am I doing this? Because classically speaking, if you see an expression like sum from 1 to minus 10, that means that that's 0. So k from 1 to minus 10 of something typically would be 0 in the classical case. But I'm saying, oh, this sum is sort of like a signed sum. And when the upper index is negative or less than this guy, I mean the other way around with a minus. Okay. Okay. Any questions about these? And so because of this definition, any sequence is integrable on any bounded domain. That is to say, any sequence is locally integrable. So this is the analog of locally Riemann integrable functions. Okay. So you see, we don't need to, in this discrete world, we don't need to talk about limits. And so far, we've been spending so much time to make sense of these different limits. And we were looking at rise over runs and how they decayed, and that gave us different notions of differentiability and all this stuff. But when you switch over to the discrete world, all of these technical matters, they go away. And as far as I understand, indeed, this discrete version of fundamental theorem of calculus precedes the standard fundamental theorem of calculus. I'm just adding finitely many things after all. Okay, now I guess I have 2 or 3 minutes left. Let's see if, for instance, the first one holds. The second one probably I'm going to leave to you as an exercise. So this is going to be an exercise, discrete analog of this. Let's look at discrete FTC-1. So I have a sequence, discrete time signal. Then I need to do the following, right? So n to m of d of x Okay, so this is, by definition, the sum from n plus 1 to m. Let's just say that m is to the right for simplicity. It works in general, but this is this. But then this is nothing but this guy. But then this is a telescoping sum. Right? So this gives me x sub n plus 1 plus x sub n plus 2 plus dot 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 plus x sub m minus, I start at x sub n, with a minus, all the way up to x sub m minus 1. So these cancel, 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 x sub m minus x sub n. So simple compared to the classical one. And a similar thing holds for the second fundamental theorem also. Okay, so that's it for today. Tomorrow, or on Friday, we're going to be really switching over to improper integrals in this discrete world. That is the infinite series. Thank you. Okay, let's start. Good morning. So, series. Now, on Wednesday, I gave you this more abstract approach. And like I said, instead of sort of only just looking at infinite sums of numbers, we're going to eventually switch over to infinite sums of functions. And we're going to start talking about analytic functions. So we had this idea of C-infinite functions, infinitely many differentiable. But somehow we would like to go one step further, if possible, and say, oh, I can just put all derivatives, all higher order derivatives of a function in an infinite sum and add them up to get back the original function. It turns out that you cannot do this all the time for any given function whatsoever, even if the function is infinitely differentiable. But when you do, when you are able to do it, the function is called analytic. You can analyze the function completely. And you can synthesize it also. But before sort of switching over to series of functions, let's start with series of numbers. So, like we said, given a sequence, let's say starting from 0, we want to make sense of this. I would like to add all of them up, give me something. And other notations for these, one thing I like is like this. I don't want to write to infinity. if I'm just denoting the lower bound, that means that you should be just adding all the terms after 0. And some people just write this. And in the next problem set, which I've uploaded like 10 minutes ago or something, you're going to see this notation. It's sum over all n x sub n. But in any event, we want to make sense of this. And I hope by this point, you have this idea that whenever you see the symbol infinity, right, supine 8, that means that there's a limit involved. And that is going to be that. And on Wednesday, we had talked about how, given a sequence, you can sort of discrete integrate it or discrete differentiate it. And so given a sequence, at least taking values in a vector space where you can add things, you can look at the sequence that is sort of like the antiderivative of it. And so when we see something like this, this really stands for the limit of the sequence that is the partial sums. Okay, so that's the definition. But maybe before that I should mention this thing, because so there's this phrase, formal sum. It turns out that it's still perhaps beneficial to think of expressions of this form even though there is no convergence. So that's sort of the phrase called formal series. A formal series is an expression of the form where x sub n is a sequence of real numbers. So whenever you see the word formal, you should say, oh, they're not claiming anything about convergence of this, or this even making sense. So when I first took this class from Professor Uger back in Turkey, he used to say, you know, it's like you can just write down anything on the board and the board is not going to object that what you're writing doesn't make sense. Of course, that's like a Bruce Lee quote from a movie, right? The board doesn't hit back. And so the board doesn't complain when you write something bad or does something that doesn't make sense. So formal series is sort of like this expression. Just formally just write it. But then if you want to actually think of it as a number, as a meaningful object, well, you look at, instead of the sequence itself, you look at the sequence of antiderivatives, so to speak. In other words, the sequence of partial sums. You say that is convergent. This formal series is convergent, and it's a convergent series if the sequence of partial sums, which are typically denoted like this, instead of using this integral of x, because it can get confusing, it's sort of like abstract, we're just going to use some other letter. So that's a sequence now. It's a different sequence of numbers. If this sequence of partial sums converge. We know what it means for a sequence of real numbers to converge. I mean it in this sense. And of course, whatever this converges to, I'm defining this infinite sum to be that. Further, in this case, we define this to be the limit of S sub n. So all this is to say that this, whenever it is defined as the limit of the partial sums. Limit as n goes to infinity, k from 0 to n, x sub k. Okay? So this you should think of in analogy with the improper integral from 0 to infinity. So this is analogous to this. Limit as, let's say, m, or rho, let's say. Rho goes to infinity of the definite integral from 0 to rho. Okay. Any questions about this so far? So let's look at some examples. Now, why would you be interested in something like this? This is, perhaps you can think of the following sort of scenario. Let's say that you're doing experiments and stuff like that, and at each sort of iteration, at each time step, you're picking up some error. And then you're trying to see if those errors eventually compound to something unmanageable or otherwise. So that's sort of one way of thinking about it. These sort of like things show up in math and sciences in general all the time. And in a sense, compared to the stuff that we dealt with so far, these are sort of like relatively easy to handle, at least in terms of like abstractions. It's just a matter of taking certain limits of numbers, after all. But at some point, they get sort of like complicated as usual, especially when you start sort of adding functions and trying to make sense of them. Now, in the case of series of numbers, there's only one sort of, or maybe there's a standard choice of what it means for it to converge. But you can imagine how, if I were to take a series of functions, then the convergence would depend on the base point, on the input value. And so then I could perhaps ask about pointwise convergence, uniform convergence, or for which values of x it converges and for which values of x it doesn't. So it does get complicated eventually, but at least initially it's not taxing that much, I think. But here, let's consider the first example. Let's start with one of my favorite series, the geometric series. So I'm going to fix, let's say, fix an alpha positive and consider sum where n goes from 0 to infinity of alpha to the n. Okay? So I want to make sense of this. I want to say if this is just a formal series or if it converges. If it converges, I want to be able to compute where it converges, right? These are the two situations. If you have a sequence, the two questions is, does it converge? And then if it converges, what is the limit? And that's what we're trying to discover here. How many of you have seen something like this before? Okay. And so what do I need to do? I need to look at the sequence of partial sums. I should mention one thing. This is like a psychological thing for me, but when the sum is over an infinite domain like this, I like to use the independent variable n. When it's a finite sum, I like to use k. That's just like something I like to do. Because I like to sort of take the limit as n goes to infinity here, so that's why I need to use a different letter here. But you can use whatever letter. I just don't like infinite k's in a sense. Okay. And so the sequence of partial sums is going to be like this, right? So S sub n is going to be the sum from 0 to n of alpha to the k. Okay. And so this is 1 plus alpha squared plus dot 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 plus all the way up to alpha to the n. Now, it turns out that I can come up with a nice expression for this by using this following algebraic trick. And so what I can do is, if I were to multiply this guy by 1 minus alpha, there's going to be some cancellations. And so opening this up gives me that this is 1 plus alpha squared plus dot 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 plus alpha to the n, and then minus alpha times the same things. So minus alpha squared minus dot 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 minus alpha to the n minus alpha to the n plus 1. But then these cancels, and then I'm left with 1 minus alpha to the n plus 1 just that. So this is just 1 minus alpha to the n plus 1. Any questions about this? You see, we're using this telescoping sum business all the time. And on Wednesday, we discussed how this is basically like the idea of the fundamental theorem of calculus. When you sort of expand certain things, things cancel out. Which means that S sub n is sub n is this. Now, of course, in order for this to make sense, alpha has to be not equal to 1. But certainly, if alpha were equal to 1, this sequence of partial sums would go to infinity anyway, so it wouldn't be convergent. So maybe you should record it. So this assuming alpha is not equal to 1, and if alpha were equal to 1, so let me just write it here, S sub n would be just n plus 1. And so, so alpha to the n would diverge to infinity. Okay? But if alpha is not equal to 1, then this makes sense. But then again, you see, in order to make sense of the infinite sum, I'm going to take the limit of this expression as n goes to infinity. And I want this to not blow up. This can happen only if this expression doesn't blow up. And that can happen only if alpha is less than 1. And so I can say that this is equal to, so it's a piecewise situation. If alpha, and in fact I can take alpha to be a negative number too if I wanted. So let me just do that. There are two cases. Either alpha is less than 1 in absolute value, or it's greater than or equal to. In this case, this blows up. In the first case, because alpha in absolute value is less than 1, its powers are going to decay to 0, which means that it's going to converge. This series is going to converge to 1 divided by 1 minus alpha. This is the quintessential example where things kind of work, kind of don't work, but at least for some alpha values, this series converges to a very nice rational function. Yeah.
If alpha was -2,
Yeah.
how would you say that the infinite sum would go to infinity?
Well, I guess I don't. Fair enough. So maybe plus or minus. Is that going to be fine? Okay. Yeah. Mm-hmm. Oh, let me just write it like this. Maybe it doesn't go to negative infinity because there are cancellations. Let me just say diverges. That's better. Maybe it doesn't go to infinity or minus infinity, or it just doesn't stabilize this sequence of partial sums. Okay. Any questions about this? Now, let's do a psychological check. Instead of writing alpha, let me just use the letter x. Okay. And so what I'm saying is that for x in absolute value less than 1, I have that 1 over 1 minus x can be written as this. I just changed the dummy variable. But the point is, of course, that when I think of it like this, I'm more prone to think of this as a function of x. Okay, so this is one situation where I have one function. Imagine I started with this, 1 over 1 minus x. This is certainly well defined in this unit interval, interval of length 1 or length 2. And I'm able to sort of analyze it as infinitely many terms. Okay. And so once we're done with numbers or series of numbers, we're going to really start looking into things like this. Now, let me ask you this. Perhaps some of you know or remember. If I had started with this function, which is well defined on minus to 1, is there any other way I could recover this infinite series? Like we started with the infinite series and we realized that we could repackage it back into this function. But let's say that I started with this function. Can I recover this somehow? Yes? No? Okay, so let's open this up. So what is this? This is 1 plus x squared. Okay, let me just open the first two. And then I have higher order terms. Now, forget about this power series or this infinite series. If I had this function, can I recover something like this? There's pretty much one other sort of instance where we used things like this, where we had higher order terms. Huh? Yes, but so that means that how could I try recovering, for instance, this from this? For instance, f of 1 is 1. Okay. This is a miracle, okay? It's really amazing. But how can I get this? Maybe there's a 1 next to it, which I don't see, of course, but 1 is also f prime of 1. Let's see. F prime. Okay, so we need to compute this. Is d by dx of this guy. And so if I were to differentiate this, minus this times the derivative of the guy inside, which is this. And this gives me that this is 1 over 1 minus x squared, which means that f prime of 1 is also 1. So maybe by just differentiating the function and evaluating them at 1, I can get these expressions. Let's try to go one step further. So if I had just given you this function so far, all we knew was that we have this tangency relationship, right? So these higher order terms were higher order compared to the linear term. But now this series gives me specific values for higher order terms too. So maybe I can try, instead of concatenating this infinite series at the first term, or the first term, I can try concatenating it at the second term. Okay. Let me do one more. So f double prime. My hope is that f double prime at 1 is also 1, because the coefficient here is again 1. Sorry, it's going to be 2, I guess. Yeah. We'll see. There's going to be a correction that has to show up. Okay. So what is f double prime? F double prime is f prime of, or the first prime of this guy. What was it? 1 minus x squared. Okay. This is this. And then this becomes minus 2 times 1 minus x to the minus 3. And then the derivative of the guy inside, which is a minus. So this is just 2 divided by 1 minus x cubed. Oh, sorry. I should be evaluating at 0, of course. At 1, it blows up. Zero. F prime of 0. Okay. F double prime of 0 is 2. So somehow I don't quite get the coefficient of x squared, but I get twice the coefficient of x squared. Okay? So at times like this, it's good to sort of do some numerology and really say that, so let's write it here. No. Let me write it like this. Maybe let me just add one more. So again, this is going to be 1x cubed and then higher order terms. So 3 or 4 and up. And now this is going to be f triple prime divided by 6. Okay. So if I were to just start with some nice function like this, and if I were to look at all of its higher order derivatives, then up to some renormalization, up to some sort of division by some integers, it seems like I can recover this infinite series. Now, you cannot do this for any function whatsoever, but whenever you can, this is called an analytic function. So f here is an analytic function. It's a function that you can analyze and write as an infinite series of higher order derivatives, or rather polynomials with adjustments coming from higher order derivatives. So we're going to say f is a real analytic function. In particular, it is C infinity. It is infinitely differentiable. Okay, it is infinitely differentiable because I can differentiate it as many times as I want, but it's more. Not only are any higher order derivatives exist, but in fact I can put them in a series and the series is going to converge. Okay? Any questions about this? Now, when we were looking at first derivatives, we were just cutting this expansion here, and this was the best. This was the equation for the tangent line, right? Now, I can likewise interpret this part as the tangent to second order polynomial, the best, parabola, the best parabola that fits to the graph of f. Okay, and it goes on like this. So we said that the first derivatives are, in the strong sense, they are about approximating by linear objects, but more generally, it's about approximating using simple objects. In this case, analytic functions are functions that you can approximate to an arbitrary degree using polynomials. Okay. Now, not all functions are real analytic. There are many functions, in fact. Most functions are not real analytic. But let's say my function is k times differentiable. If my function is k times differentiable, I should be able to, instead of sort of opening this or writing the series to infinity, at least the k steps, I should be able to write it down. And so that's the content of Taylor theorem, Taylor approximation. And so we're going to spend some time in the last week, so week 14, the week before the reviews, on this theorem. It's a very useful theorem. But before that, we should spend some more time on numbers and this type of a formalism. Any questions about this? This is a very convenient thing, you see. It's like, on the one hand, it's a bunch of like infinitely many numbers. You try to add them up. And it too has certain implications. But on the other hand, it also allows us to sort of like approximate functions to an arbitrary degree when it does work. Okay, so this was one example, geometric series. Another example, oh, maybe I should mention this as well. You see, this function, even though in order for this expansion to work, I need to restrict x to -1 to 1. But of course, this function is well-defined insofar as x is not 1. Right? So I can plug in f of 15 if I want it. But what I'm saying is that for x equals 15, this doesn't quite work. Okay? And so this has to do with what is called the radius of convergence. So in this situation, for instance, we're going to say that the radius of this power series is radius of convergence is 1. So somehow this expansion works, but again, locally. It doesn't work globally, but just like with derivatives, you always have like a certain localization. You need to localize so that you can approximate. Okay, so here's the next example. So this was an example of a series that converges. And here's a standard example of a series that doesn't converge, the so-called harmonic series. So the first one was the geometric series, where I added powers of one number. And the harmonic series is when you add reciprocals of integers. This is called harmonic because it has to do with some musical stuff. You can read on Wikipedia about all that stuff, but harmonic series. And so this is a series defined like this. Let's say at 1 to infinity. This. Okay. Now this is a formal series. Again, I need to figure out if it is convergent. And if it is convergent, I need to figure out to what value it converges. Now it turns out that this is not convergent, but somehow it's still important to think about it. Okay, I'm going to say a couple words about it in a second. And so again, I'm going to look at the sequence of partial sums. So I'm concatenating at some finite time n. And so this just is this 1 plus 1 over 2 plus 1 over 3. Let me open this up a little bit. 4 over 5. One over 6. And it goes on like this all the way up to n. The claim is that this is not convergent because of the following simple argument. You sort of look at the powers of 1 over 2. Okay, so this is one power. This is the other one. And I have here this. And I have here this. You can do other powers as well. But this was the argument given in the textbook. So I'm just going to stick to that. Now, instead of 1 over 3 here, if I had 1 over 4, the partial sum would decrease, right? Because 1 over 4 is less than 1 over 3. So if I were to replace 1 over 3 by 1 over 4, this would decrease. And likewise, I could replace this, this, and this by 1 over 8. Again, I would have the partial sum decrease. And I'm going to collect these terms like this. And then, for instance, the next terms, I'm going to sort of switch with 1 over 16, and then 1 over 32, and so on. And the point of doing this is that now this sum is 1 over 2. And this 2 is 1 over 2. And I'm going to have many other 1 over 2s. And so, for instance, if I were to look at a partial sum where n is of the form 2 to the k, then I'm going to have some finite number of 1/2s added up at the very least. And that's going to be a lower bound. But this has to diverge because I keep adding the same term over and over again, which is a positive term. So this sum, there's no way for this sum to converge. It's going to strictly increase. So this goes to infinity as n goes to infinity, which means that there is no way for this to converge. So the harmonic series is divergent, diverges to infinity. Okay? Now again, we've been seeing this pattern over and over again in this class. And if something doesn't quite work, we don't sort of say, okay, we don't admit defeat and just do something else. We try to still make sense of it. And the way one can make sense of this, there are multiple ways, but one way of doing it is to say, oh, maybe there's an issue here. So these terms decay, but maybe they don't decay fast enough. Well, if I were to have a slightly larger exponent than 1, then hopefully this would decay to 0. And so let me introduce a parameter alpha. Or maybe let's just look at the reciprocals of squares. The general term for this is p series, and you look at the pth exponent, but let's just look at this one. Amazingly, it turns out that this is convergent. Okay? And one way of seeing this is the following. We can try using, we can sort of approximate this discrete sum by a continuous sum, in other words, by a Riemann integral that is improper. And perhaps using the power of calculus, we can say something about it. And so, thinking about this, I have something like this. So here, this is 1/x squared. Okay. And then I'm looking at the integer points. So this is 1, 2, 3, 4, 5, and so on. Now note that this sum, let's just look at a partial sum, S sub n. So this is 1 plus 1/2 squared plus 1/3 squared plus 1/4 squared all the way up to 1/n squared. This sum is the area of finitely many rectangles in this picture. So it's this plus the area of this, and then the area of this, and then the area of this, and so on. Okay. Now, without evaluating, what I'm saying is that the sum of the areas of these 5 rectangles, for instance, is S sub 5. Okay. Well, that means that I can, based on the picture, instead of trying to compute this infinite sum and see if it converges, I can try to compute the indefinite, or rather improper integral of 1/x squared. And then if that converges, certainly based on the picture, because the integral of f here should be the area underneath the graph, certainly that sum should dominate this sum. Okay? And so this is going to be like this. So let me say it like this. Of course, this guy we discussed on Wednesday, so that its integral diverges if I were to try to integrate it here. But there's no problem if I were to try to integrate it over here. And that's what I'm going to do. I'm going to get rid of this part because I know that this rectangle contributes 1. And then I'm going to try to look at the contributions coming from the remaining rectangles. So this is 1 plus the integral from 1 to n of f of x dx, which is this. So f of x is 1 over x squared, an antiderivative of it I can compute, right? If I were to differentiate this, it gives me x to the minus 2, which is f. So this is an antiderivative. And then the fundamental theorem gives me that I can just evaluate this at the endpoints. 1 plus, now what is this? Minus 1 over n minus 1. Yes. So 1 plus 1 minus 1 over n is 2 minus 1 over n. And of course, each of these terms are positive numbers, which means that the partial sums are bounded by 0 as well. And so that means that by the squeeze theorem, it has to converge. Okay? And in fact, because this converges to 2 as n goes to infinity, this sum can be at most 2. Cannot be greater than 2. So 1 to infinity. Okay. Of course, if I wanted, I could have used other sort of exponents and stuff like that. And in fact, when you really start incorporating this exponent as a parameter, or maybe, in fact, as an input value to a function, now things start to get interesting. Definition. The Riemann zeta function is the formal series zeta of s. S is your parameter. You look at this formal sum, where s is some parameter. So somehow, as you vary this s parameter, so we saw, for instance, that zeta of 1 is infinity, it blows up. Zeta of 2 is some finite number. And some people can compute this explicitly as well. There are certain formulas that allow you to do this. Basel problem and stuff like that are important sort of relevant questions. But at the very least, somehow it turns out that where this formal sum converges and where it doesn't, tells you some important stuff about very foundational ideas, especially about the distribution of prime numbers. Okay. And so we showed that zeta of 1 is infinity, zeta of 2 is finite. So you would say that this zeta function has a pole, it blows up at 1, and it gives you a finite value. And it turns out that instead of just considering s as a real parameter, it is more convenient, perhaps, to think of it as a complex parameter. But we haven't used complex numbers in this class, so I'm not going to mention that. But let me leave it to you as an exercise. If S is greater than 1, then zeta of S is convergent. Then so somehow the poles of this function, or this formal series, when it blows up, as well as where its zeros are important sort of ideas, important pieces of information. Okay. Any questions about this? Okay, let me just leave with one sort of statement. This is a theorem in the textbook, but I'm just going to leave it to you as an exercise. It's not too complicated. Which says that if I have a sequence of numbers whose formal sum converges, then in fact that sequence has to go to 0. Okay, this is a nice exercise. The other way around doesn't quite work because we just saw an example, not conversely. X sub n defined as 1 over n goes to 0, but the sum diverges. Okay, so this only works one way. Okay, thank you. That's it for this week. Next week we're going to continue.